Thanks for the introduction, Matthew. Hi, everyone. Welcome. This is Chong Xiao, a software engineer in Uber Michelangelo team. In this talk, we will briefly introduce how Uber Michelangelo platform embraces large language model ops with support of Ray. This work is currently being actively developed at Uber by Michelangelo team engineers, including Bo, myself, Annette, and Jape. Firstly, I'll introduce how we bridge the gap between Michelangelo and large language model ops from a high level. So let's look at how Michelangelo looks like before large language models. Michelangelo is Uber's internal end-to-end machine learning platform. It enables machine learning developers to prepare data, train and evaluate models, deploy models, make predictions, set up auto-retrain pipeline, and monitor model performance in production. So Michelangelo started to integrate Ray since 2021. And as of today, both deep learning training jobs and XGBoost training jobs are running on Ray clusters in production. We have seen a few important benefits of switching Ray, such as Ray provides powerful primitives for distributed computing, including decorators for remote tasks and APIs for distributed memory store. And also Ray supports heterogeneous cluster auto-scaling, and lifecycle management, which is very critical for tuning workflows. And also a lot of popular machine learning libraries have been integrated into the ecosystem. And this allows Michelangelo to pick up the lowest hanging fruits. Fourth, Ray also provides first-class Kubernetes support. This aligns with Uber's ongoing efforts of moving our computing resources into Kubernetes cluster. Compared with Ray and before 2021, we have used and explored other alternatives in the past, such as MPI and Spark. For MPI, it is straightforward to spawn data parallelism jobs for machine learning workflows, but it lacks support for resource management. For Michelangelo was using Spark machine learning pipelines for training before 2021, and the Spark estimator class is consistent for offline training jobs and online prediction jobs, but we encounter a few challenges like separating CPU, GPU jobs, and lifecycle management. And also, Michelangelo team has spent a lot of effort to make deep learning framework like TensorFlow and PyTorch be compatible with Spark estimator class. This part of work has been open sourced to Harvard Git repo under Spark folder. Large language model have recently gained a lot of attention since the release of ChatGPT around the end of 2022. Uber has started to apply large language models to a few important use cases, including both pre-training and fine-tuning scenarios. These Gen AI use cases include internal developer-facing case like Code Copilot and external customer-facing case like customer service chatbot. Development platform engineers are developing coding assistants by pre-training open source model like StarCoder and CodeLlama using Uber's internal code repos. Such coding assistant can provide autofill suggestion as well as task suggestion to improve developer productivity. Custom obsession team have launched Generative AI to support three cases: context summarization, summarizing the context faster and more accurate to save agents time; FNQ chatbot, response questions in a conversational manner instead of just giving help articles; response generation, provide more personalized and in-context responses instead of using static saved templates. In order to onboarding Gen AI cases to Michelangelo, it requires Michelangelo to support large language model ops to encompass the practices, techniques, and tools used in production environments. The common components of large language model ops, including exploratory data analysis, data preparation. To note that data preparation is one of the most challenging stages our model scientists have encountered today when applying large language models. Prompt engineering, model pre-training, model fine-tuning, model review and governance, model inference, and model monitoring with human feedback. On one hand, users can choose to use closed-source large language model ops platform and one-stop solution. On the other hand, users can also use popular open-source solutions such as Ray, Hugging Face, DeepSpeed to fulfill their own needs. Both open source and closed-source solutions have their own advantages and disadvantages. In common sense, open source solutions have good community support. The implementation is transparent because the code is accessible, and the cost usually is free. But it comes with disadvantages such as lack of technical support. The community-driven approach can lead to faster development and innovation, but it also can lead to lack of quality control. It has fragmentation issues since it's hard to ensure everyone is using the same version and with the same features. I want to call it here, this is common sense for open source solutions. With the Anyscale team support with Ray, we haven't run into any of these issues with Ray yet. Meanwhile, closed source solutions are good at quality control, providing technical support and better security check. But it misses the transparency because the code is inaccessible, and it requires to pay for a license to use the software and the limited features that are provided by the owners. By considering Uber's own business needs and engineering requirements, Michelangelo chooses open source solutions to build large language model apps. So we are facing a few challenges supporting large language model apps on Michelangelo, including existing internal limitations and external integration challenges. The internal limitations is about how to onboard large language models on Michelangelo. Michelangelo lacks the model parallelism support, which limits the number of the model parameters by the GPU physical memory. Michelangelo also doesn't have a good end-to-end support for Hugging Face PyTorch models, especially tokenization part. In the past, we have observed a few issues blocking Hugging Face model to be servable in online service environments. We are also facing a few integration challenges with Uber's computer architecture, such as the storage part. We want how to connect Uber's internal storage like Hadoop and TerraBlob when training open source large language models. TerraBlob here is Uber's centralized solution to store blob data. And the hardware part, how to distribute a large language model training job to most powerful GPUs in-house or on the cloud. The software part, how to integrate multiple open source libraries with Uber's production containers. Beyond this, since large language model training involves massive computing resources and hours, an agile development environment to accelerate both development and debugging purpose is desired. So we list a few open source libraries here as our major building blocks for large language model ops journey at Uber, including Ray, Hugging Face, PyTorch, DeepSpeed, TensorRT, and Triton Inference Server for serving, and bits and bytes for quantization. In general, Uber's end-to-end machine learning ops are achieved by integrating Ray-based large language model training framework into Michelangelo Studio. Michelangelo Studio is Uber's one-stop solution to build, train, deploy, monitor, and debug models. Many features to Michelangelo Studio can be reused here, and the rest of the talk will focus on the design of Ray-based training framework. Our large language model training architecture is as shown here, from top-level retrain API to bottom-level LeetCode library. Retrain provides a single API to perform distributed training using PyTorch on Ray cluster. In particular, Retrain handles the setup of distributed process group in PyTorch, enable users to run their training script in data parallelism fashion. Hugging Face Transformer provides the API to download and train state-of-the-art open source transformer-based open source models. This capacity allows Uber developers to efficiently work with the most recent open source models with minimum effort. DeepSpeed is a popular deep learning optimizing software supporting model parallelism for PyTorch models. We choose PyTorch as a deep learning framework because most of our SOTA open source large language models and techniques are implemented in PyTorch. Anyscale implements the multi-GPU and multi-node communication optimization for NVIDIA GPUs and networking. So today, large language models are trained on our in-house A100 clusters as below. Each host is equipped with 4 A180 gigabytes GPUs and 2 Intel Ice Lake CPUs. In future, we are planning to extend this training to cloud-provided GPUs. We provision the Ray cluster on A100 GPU using Michelangelo job controller, as shown on the right of the slides. Federated scheduling scheme send job requests to multiple Kubernetes clusters. The job request is a gRPC call generated from end-to-end workflows, notebooks, and CLI commands. A dedicated cluster receives the request and spins up the Ray cluster using open source kubeRay operator. In addition, elastic resource sharing is implemented so we can reallocate available resources to high-demand resource pool as shown on the left of this slide. We have built an interactive development environment on Ray cluster. A Jupyter Lab environment is enabled. This allows our developers, our model scientists to edit source code and the model configuration file on the fly and reuse the same Ray cluster to run multiple jobs. Ray dashboard is also enabled, so we have better logging and system monitoring support. Now I'm giving the rest of the time to Bo to talk about the ray-based training design and integration in details.
Yeah, thanks, Drew. Yeah, hi everyone. My name is Bo, also from Michelangelo Uber AI team. Now I will talk about ray-based trainer design and integration with the Michelangelo existing components. So first of all, let's talk about the training pipeline design. So at a high level, our training pipeline design containing 3 stages: data loading, distributed training, and model checkpoint management. So let me first focus on the distributed training part. So we use ray torch trainer to start multiple reactors, and in each reactor, we make sure the torch process group already configured for distributed training. And each reactor will do its own training loop, and using Hugging Face trainer and Hugging Face dataset. And in Hugging Face trainer, we rely on deep speed to do model parallelism. And we rely on Hugging Face accelerator to manage the partitioned model states and do gradient updates. Now let me talk about how we do the distributed data loading. So first of all, we ensure each reactor only work on its own dataset, including train and eval. So the train and eval dataset do not mess with each other across reactors. So for data source, we support reading the large dataset from Hadoop, which is very important for pre-training because pre-training dataset is very large. We also support reading dataset from Terablob, usually for small dataset. That's very important for supervised fine-tune because supervised fine-tune dataset is usually small. We also support reading dataset from Hugging Face. That's very important for our developers to testing the code and do active development. In terms of file formats, we support Paquet because Paquet most of the time is default format on Hadoop file system. We also support JSON list, which most of the time using Terablob. For tokenization, we support streaming tokenization, basically tokenizing on the fly during training. That's important because for large language model pre-training, the dataset usually is very large. People want to see how the training goes on the fly. We also support pre-tokenization and local cache. That's most of the time used often in the supervised fine-tune when the dataset is small and on Terablob. So let me talk about our ongoing effort on model checkpoint management and fault tolerance. So usually the large language training is very costly and also time-consuming. You need to use hundreds of GPUs and train weeks to months to get the final output. So if anything fails in the middle, our developers definitely don't want to start from everything from scratch. So instead, they really want to find the failure point and resume from the corresponding checkpoints. To implement that, we periodically push the data snapshot and the model checkpoint to our remote storage on Terablob. And when the user wants to resume from the failure point, we ensure each reactor could download the data snapshot information and the model checkpoint, including model parameter and the checkpoint. Then they can continue its training. So now let me talk about our logging and profiling system. So Michelangelo already have a logging system with a Comet. So we are able to integrate large language model training with Michelangelo existing logging framework Comet. So this is actually very important because during developing, our developers really want to see how the training goes during the training, not the end of the training. So they can monitor the metrics, especially the loss, monitoring the resource usage, so they can adjust the batch size and other hyperparameters. We also enable the torch profiler for advanced developers, so they can debug under the kernel level, and they can do more model optimization. So with all those developers, we can show our preliminary result. So first of all, we can train Llama 2 70 billion on 32 GPUs. Secondly is we find the linear scalability when we train Llama 30 billion models, when we're increasing from single host to multiple hosts. That actually is very cool for the linear scalability. Last one, we actually support pre-training, which is a concept in large language model, supervisor fine-tune, also parameter efficient fine-tune, which is a LoRa and QLoRa. And people only need to change a few lines of code to switch between all these cases. Here I give a plot that shows how our evaluation metrics, the loss metric looks like. The key learning from here is for fine-tune always gives you the best result. You can see from the Llama 2 70 billion and Llama 2 30 billion result. And also, even though the 4 parameter fine-tune is the best, but in terms of resources and time, it's actually based on our benchmark is 4 to 8 times slower than LoRa and QLoRa. More than that, you need more resources. For example, Llama 2 70 billion, you need at least 32 GPUs to train if you want to train with a 4 parameter update. But on the QLoRa, you only need a single GPU to train it. Okay, after your model training, what do you want to do next? You want to do evaluation and decide whether to put online for serving. So in order to do that, we also using Ray to do offline model prediction. So we build a very simple APIs, which is input data, pre-trained model, output destination. We integrate all this with Ray. And across different reactors, we use a data parallelism. But inside each reactor, we use pipeline parallelism. If the model is too big to fit a single GPU, we need to use multiple GPU in each reactor. So after the model prediction is done, you want to do evaluation. We integrate large language model evaluation with a Michelangelo Studio existing evaluation framework. So our customer can view the aggregated metrics to decide how good is the model. We also support the instance level metrics. Here I just give an example of our customer's evaluation metric, which is for the chat summarization, which Chongxiao mentioned before. Okay, after evaluation, people find, okay, my model is good. What to do next? They want to deploy it. So we reuse Michelangelo existing deployment pipeline, which is including model validation to see whether your model missing anything, right? Model packaging to see, okay, if I want to model TensorRT for the model, you need to do packaging. Model uploading, the model deployment. In model deployment, we use Triton server and TensorRT to serve the large language model. Once the model deployed, our caller will call our service through Michelangelo API gateway. The Michelangelo Gen AI gateway basically routes the large language model service to the corresponding large language model server. And then large language model server basically log in the input and output text to Uber M3 storage for monitoring and debugging. So this is just a snapshot show you how easy the deployment of large language model to be. Because we already integrated with the Michelangelo existing model deployment API in MS Studio. People only need to create a deployment button, then their model will online. So after their model is deployed, they can do live tests, say, okay, how is my model looks like? Anything wrong? With all that, I will hand over to Chongxiao for takeaways and our learnings.
Thanks, Bo, for the details of our training pipeline and the evaluation part. Yeah, there are a few valuable takeaways we have learned from this project. This project just started in June. It's just in current shape, it's only takes the effort less than 3 months. So firstly, we are leveraging the extensible Michelangelo framework to support large language model cases with a new Ray-based large language model training framework. We didn't start everything from scratch. We use everything possible already existing in Michelangelo. Secondly, we show that an end-to-end large language model ops is built possible with open source solutions. And also, we recall all the real benefits we have really highlighted in the beginning of the slides. It's already show up again in our new large language model training framework. So last but not least, I would like to give acknowledgement to both Uber and Anyscale team. So without the great collaboration, it is impossible to make this project in current shape within 3 months. I would like to thank you for the quick response and support from Anyscale folk, especially giving credit to Matthew Dinh to help us fixing a few PyTorch distribution issues on Ray open source repo. I would also like to thank the Uber Michelangelo team for unblocking upstream and downstream stages of large language model ops. We cannot be here today without all the support above. Yeah, that's all for our talk today. Yeah, I'll leave the time for the question.
Cool, thank you so much. Yes, so questions. We'll start over here.
Thanks for that presentation. Quick question that on your serving piece, I know that you're using Triton server for serving your LLMs.
Yes.
Can you talk a little bit about the motivation behind that?
One thing is learned because in production today, Uber's model, deep learning model already served in Triton inference server. So we see very good performance, and we have very collaboration with NVIDIA. And NVIDIA just taking one step further, they are preparing the TensorRT LLM repo and want to optimize the performance with in TensorRT side specific for large language model. So that's our decision goes right now. Yeah.
I have a quick question for the evaluation part. Can you go back to the slide? Like in terms of the score that you calculated, how did you come up with the scores?
How do we come these scores? Yeah. So first of all, the evaluation of large language model is very different from traditional machine learning model, because most of the time traditional machine learning model basically binary ranking, right, linear regression. You have standardized metrics. So for this particular case, which is chat summarization, we care about how your summarize reflect your original chats between agents and the customer. So those metrics are defined in the Stanford, I forget that, ROG repo. Basically covers how accurate your summarization it is and how concise it is. And there's another one I forget. So basically that's how a customer can define those metrics. The nice thing about our evaluation is we allow the customer to define their own instant level metrics. Michelangelo only manages the aggregated metrics and the final MA Studio display. So as long as the user, our customer, write their own instant level metrics in certain format, input output, then Michelangelo can take over it and display and do aggregation for them. Yeah, does that answer your question?
Is that based like human-based eval?
Oh, you are saying that how do we get the response, right? Oh, yeah. So there are two things. We first of all rely on human level data. Secondly, we also use the GPT-4 to generate those, compare with GPT-4. Yeah.
Thanks. I might take it wrong, but it seems you've reused a lot of the Michelangelo features already, except the training and fine-tuning of the LLM. Just wonder if that's correct, and if that's correct,
yes.
What takes you to this decision, and if you have any plan to integrate the LLM training and fine-tuning into Michelangelo? Yeah.
So this is already part of Michelangelo. So some of you might see the previous year, the resummit talk Uber held last year. So the major important part is the model training part. So Uber has its own framework on Ray, but it's running on Harvard for data parallel support. That's the things currently in production for recommendation models and the simple NLP cases. But however, we found that framework cannot fit into the case here for two blockers listed here. One is the model parallelism, because Harvard don't support model parallelism. Second is the Hugging Face end-to-end support. We found our model server pipeline in existing Michelangelo. They have a few blockers for serving Hugging Face tokenizers. So instead of fixing the things on the old side, we found that it's very convenient to taking the usage of rich API starting from scratch, adding the support to the new large language model framework. But for your question, how to integration back, we are working on that. So this work today is most of our users, they are using, most of our users and model developers, they are using this UI, like this Jupyter interactive Jupyter Lab environment to edit the file, to edit the model configuration file, submit your job. But we are integrating things back to Michelangelo Studio. So this will become a new trainer called large language model trainer, and the user can click a button on the Michelangelo Studio and kick out the train. User don't have to go to this interactive environment and run the job.
Yeah, I can add a few points. So Michelangelo is very general. So it has a high level, API level, unified API level, and also have on the bottom has something, each component. And under each component, it also has some algorithm. So for large language model training, basically we kind of using Ray and the open source model to have in the algorithm part to replace the trainer part. But at the top level, in terms of the component, and also at the high level, unified API, because we define the protocol is general enough, such as any kind of very low level development can easily plug in back to Michelangelo. Yeah.
Answer.
Thanks so much for the presentation. I'm wondering if you can speak more to the API. Specifically, I'm a little unclear on what Michelangelo abstracts away from the user. Like, for just concretely, would the user need to know Ray in order to use Michelangelo for this purpose?
No, user. So let's say if user knows what kind of data source he needs, what kind of feature he needs. So he just named the data source, name of the feature. And the user, if he want to pick up one of the open source models for retrain, he can specify that in the YAML and kick out the end-to-end workflow without knowing Ray. Michelangelo take care of launching Ray, pipelining the training job with other data preparation and transforming stages internally. And what's user-facing is just this Michelangelo Studio UI. This is only our customer-facing part. So they don't have to know. But today, the initial version of our large language model training framework is we first presented this Jupyter-based interactive environment to our alpha users. So because they are kind of users know how to write a code, how to configure a file, so they first kick out their model training with by writing the code. But eventually, user don't have to. User will be pure on the data science level, specifying data source, the model want to use, and the features.
I was wondering, how did you get that Ray dashboard at the bottom of your Jupyter environment? Was that a custom widget, or was that available from the Ray API?
It's a good question. It's not on the same address. So Jupyter Lab has its own pod. Ray dashboard has another pod. So it's not like this. Actually, two screenshots. Yeah.
So you photoshopped it. I see.
But a
Okay.
good catch. Yeah.
You tricked me.
Yeah.
Cool. We have time for one more question, if there are any.
The batch scheduler seemed like a really cool addition to the stack. Are there any plans to maybe open source that at some point? It seems like a good alternative to like Volcano or some of the other Kubernetes batch schedulers out there.
I think it's possible. We don't close the door. I think the Michelangelo is considering about open source the whole Michelangelo repos to public. I think this job scheduler will be part of it because we call it MA job scheduler. I think, Travis, if you are interested, we can talk with me offline, the principal engineer in Michelangelo.